Okay, I think we should get started.
Everyone, I'm Robert Crow. I'm a developer advocate on the TensorFlow team, and my focus is really production ML and TFX. So we're going to be talking today about distributed processing, and with me today is Reza Rockney, and he's going to be we're going to be trading off. So I'll start off, and then Reza will talk, and let's go ahead and get into it. So let me start my slides. Okay. So, and the focus here really is on distributed processing for machine learning. So there's a lot of uses for Beam outside of machine learning, but today that's what we're focusing on. And usually when you think about ML, if you're a data scientist or an ML engineer, or you're just starting out, you tend to focus on your model and what kind of results you can expect to get from your model, and what sort of data you have available to train your model. And that's great. That's certainly very important. It's the heart of things. But when you get into a production environment, you discover that your model might be typically like 5% of your code, and the rest of the ingredients that are required to make it part of a product or solution that you can support over time and offer to customers reliably, that's actually a much larger effort. So that's a lot of what we're going to talk about today. And people have discovered this the hard way, unfortunately. This is pretty typical. Usually the first time someone puts something into production, they have an experience like this where they they after 3 weeks they had the model and then they thought they were done, and 11 months later they're still working on it. So here's the issue. In machine learning development, you have all the traditional challenges that you have. Assuming you're doing supervised learning, you're going to want labeled data. So you've got to figure out somehow to label your data. You're going to have to worry about just the data set that you have. Does it cover your feature space? You want to minimize the dimensionality, and you want to make sure that it actually has predictive information in it. You should be worrying also about fairness and whether different parts of your community, your users, are served well or equally well, or at least as well as they can be. And then in certain domains, you have rare conditions. Healthcare is a prime one for that, but also finance, where you have situations that may occur very rarely, but they're very important. And the data lifecycle management becomes increasingly important. After you do your first deployment, you discover you're going to have to, your data is going to change, and you're going to have to change your model along with it. So you've got all that to deal with, but then you're putting
Robert,
a piece. Yeah.
sorry to interrupt, but I think you're not sharing your slides.
Oh, well, that's not good. Okay. Thanks. Okay. Am I sharing now?
Yes.
Yes.
Okay.
You still only into your first option, buddy. Don't worry.
Okay. Let me just back up a little bit. So and present. When you start out, you tend to focus on your model. You discover that your model, might be typically around 5% of your code. So there's all these other things to worry about. This is a tweet from someone who discovered just how hard it is. They had a model, and 11 months later, they're still working on it. And these are the challenges I was just talking about. So in machine learning development, you have all these challenges, but you're also putting a piece of software into production. So you have to worry about this, the things you worry about anytime you put a piece of software into production. Is it scalable? Can I reproduce the results? Is it modular? Am I going to going to be able to test this? And safety and security as well. In ML, there's attacks that can happen just like any other piece of software. Google's got a lot of experience with this. We've been putting machine learning applications into production for quite a while now. And a lot of it, I'm part of the research organization within Google. A lot of it has been driven by original research that was done at Google to learn how to do this. So there's a lot of papers here going back to as far as 2015, but I mean, you can go back well before that too, if you'd like. And it's great stuff. If you want to learn more, these are great papers to learn from. There's also now a continuous deployment foundation that has started looking at ML ops, and they've published this architecture as sort of a reference architecture. It's okay as an architecture. I have some issues with it, but it's a good starting point. And this is the architecture of TFX, or TensorFlow Extended. So this is the basic building blocks that form TensorFlow Extended, and you can look at it in a couple of different levels. So we'll get into that. TFX is used across Google, and not just Google, but the other alphabet companies as well. You probably recognize some of these icons. TFX is the majority of the ML that is put into production at Google. And our partners as well. So you might recognize some names here, including Twitter, which has a nice blog post explaining how they made the choice to move to TensorFlow. They were actually moving from a torch-based environment. So when they went out and did the evaluation, they evaluated PyTorch, they evaluated TensorFlow, and really it was the strength of the production offering and the rest of the TensorFlow ecosystem that made it pretty clear to them what their choice should be. Okay, and now Reza.
Hey, thank you. Let me just quickly share my screen. Okay, I'll need to wait for you to finish that. Fantastic. So share here. Can everyone see my presentation? Yeah. Yes, Robert, is my presentation showing?
Yeah,
great.
That is, yeah.
Thank you. A very warm welcome from here in Singapore. It's my evening here, and thank you, Rob. So what we're going to do in this section is, for folks who may not be familiar with Apache Beam, we're just going to do a high-level overview of Apache Beam and how it ties into TFX. And after that, I'll be handing back over to Rob, who'll go through the core of the TFX components in detail. Apache Beam is a unified programming model for batch and stream processing. It's portable across execution environments. We'll go through a little bit more detail of that in a moment, and extensible. So you can have shared new SDKs, I/O connectors, so the input and output into the system, the sources of data, and the transformations. And actually, the transformations is part of what TFX has done by building libraries that others can use. And I've been working with Beam since the start, and as well with Google Cloud Dataflow, which is the product that I am a developer advocate for. One of the things about Apache Beam that I really like is the vision that it has to allow developers to use the programming language of choice, what they prefer to spend their time on, to be able to build sophisticated, complex pipelines using very expressive primitives, and then have that pipeline, once defined, be able to be executed on their execution environment of choice. So Google Cloud Dataflow for a cloud execution, Apache Flink, Apache Spark, Spamza, these are all choices, and there are others. And if you go to the Apache Beam website, you should be able to see all the other runners that are available. This freedom is what enables TFX to actually build their data processing part of their components on top of Beam. So Robert will go through these in detail, but data ingestion, validation, transformation, and model analysis, these all require data processing. By doing it on Beam, what they get are the benefits of, for example, being able to scale out after you've done development and now we're going to production. Scaling out becomes not a problem because the runners take care of distributing all the work and the files that need to be processed, all the streams that are coming in. So essentially, by putting this on top of Beam, TFX gets immediate access to everything that the Beam ecosystem makes available. So in terms of execution environments, in terms of I/O connectors, in terms of all the other work that's going on by the Beam community. So the TFX essentially becomes a framework on top of this framework, which is fantastic. Just to go through a little bit about the pipelines and how you build a pipeline, again, for those who may not be familiar with Beam, there are three primary components. There's a P collection, which is an unordered set of data, for example, the input and output. This P collection, you apply parallel transformations to it, P transforms to it. So you take a P collection, and a parallel transform can be done against one or many P collections. You apply something to it. For example, you may shape data, you may enrich data, you may validate it, and then the result of that transformation becomes another P collection. And these operations you put together within a pipeline. There's a serial pipeline showing below, which is, a fairly standard thing that we may want to do. So the first transform that we do is a source transform that's reading from a database table. This generates a P collection, and the P collection, then we do some transformations. For example, we could be doing enrichment by calling an inference API and enriching that data. That generates another P collection, which we then are using a write transform to write into a database table. Now, I'm going to go through and build a small pipeline, just to show how that's done with Python. I do most of my work in Java, which would make it much more verbose. So Python makes it much nicer and fits on the slide. Just to get a bit familiar with the syntax. So the pipe operator has been overloaded to call the method apply, and the write shift operator has been overloaded to set a label. So if we look at that first example there, the P collection. So P collection pipe, so taking that P collection and applying the transformation that's on the right-hand side, and that transformation we've called add one, so that's the label that we've applied to it, and the transformation itself is pretty straightforward. It's a lambda function that's just adding one to every element. So with that in mind, let's go ahead and see what it looks like to build a pipeline. So in this example, let's assume we are a retail company, and we have both online stores and traditional bricks and mortar stores. Both of these are generating files. We'll do this in batch first, and then we'll show how this can be translated into stream later. So they're generating files. In these files contains information about sales, which happens to include an item ID for the product that's been sold. And what we want to do is count the top 10 sales. So first thing we need to do is actually read these data sets in. Now, the data sets live in two different locations. So what we're going to do is create two parallel collections, P collections. The first one, we're going to use P stands for pipeline in that top line. So P and we're going to pipe and apply the read from text source to it. That will read the text information line by line from our files. We notice we actually construct the pipeline by building another pipe straight afterwards. So beam.map allows us to then transform that data. And what we're going to do essentially in that lambda function is just take out the item ID, for example, from the data that we read. The data could have been JSON format. It was a parse of the JSON, and then pull out the item ID. In the next piece, we create the online sales P collection. So this is very similar to the other one, but just coming from a different location. Now we have two P collections, and we need to just bring them together. So we're going to use a beam primitive to do that. And so we pass them to beam.flatten. And what that does is just brings those P collections together as one, which allows us then to do some analytics. The first piece of analytics we're going to do is going to use a combiner. And the combiner, what that's going to do for us is per key count the number of items. So that number of times an item shows up, it's going to count the number of times that has happened. With that data, we then pass on to the next transform, which is another combiner that gives us the top 10. So here we've gone through a bit of analysis. And with that, what do we do with that data? Well, we want to output it somewhere. In this case, the top sales is getting output to BigQuery, Google Cloud BigQuery, as our data warehouse. So there it's moving the data there. Now, if you look at that whole flow, and we come back to thinking about TFX, so TFX, and Robert will run through this, has a set of libraries that the components are built from. So those libraries, one of them is sort of analyze and transform data set. If we look at this pipeline, it's actually not too dissimilar to the one we just constructed before. There is some CSV files that are being read. We are reading them as text. Then we are doing some parsing. And then we are passing it with this one line to analyze and transform along with a processing function. This particular example comes from the TFX website, and you can go there and actually see the full example in detail. But the cool thing here is up to this point, you could have been coding Beam, and then you're just pulling in this library and making use of it. Now, that single line of code is actually doing a lot of things. Back to Rob's point about only 5% of it is the model piece. That single transform, I ran that on Google Cloud Dataflow and expanded that transform so I could see all of the components that make up that transform. And we can see there is a lot of boxes compared to that one box. So all of those extra boxes are the interesting business logic and learnings that the TFX team have had in operationalizing ML, and being able to bring that in and make it easy for end users by just giving you a simple line to make use of. So let's go and have a little bit of a look at some of the primitives that exist within the Beam ecosystem just to build up our pipelines. The first one, very common, is element-wise transforms. So taking an element and doing something with it. In this example, we are taking words and we are creating a key-value pair using the first letter in the word as the key. At this point, we could be doing some feature extraction, or we could even doing some enrichment, and that enrichment may require bringing in some other data, which we'll come to in a moment. Another primitive would be group by key. Now that we've got some keys, we may want to group them together. Here we can do the group by key operation. What we'll end up with is a key value where the value is an iterable that we can work on. Now, in theory, the count that we did previously, we could do with these primitives. We could do a group by key and then just manually add up all of that iterable values if these were numbers and get to our count. However, that wouldn't be the ideal way to do it. The best way to do it is actually use a combiner. Because this data is all distributed and something like sum or count is cumulative and associative, we can do it anywhere and the result will be the same. What we can do is using that combine, which we did when we built that pipeline. In the combiner, on each host and that is running the code, it will initialize an accumulator, and then as inputs are coming into each of the workers, it's going to add those values to the accumulator and eventually merge those things together in exactly the same way that we saw when we did that sale count. Those were primitives around, actions that we do on the elements, but also the graphs that we want to build. So remembering the TFX library, that was the very large graph distribution. Most interesting things that we want to do with the pipeline end up being these complex graphs. So there are very easy mechanisms to build these things with Beam. First one is branching, very straightforward. You've got a simple P collection and you want to do multiple things with that P collection. All you need to do is apply a different transform to the P collection and you get your branch within the pipeline. Another piece that we may want to do is, given a single element, we may want to output to different locations. The very common usage of this is the dead letter pattern. So let's imagine that the JSON we get is not clean. Sometimes it fails to parse. Now, we don't want to just throw that stuff away or dump it in the logs to have to decipher afterwards. What we can do is actually, when there's a parse failure, just catch the exception and send that output to somewhere else. Quite commonly, we send it to a host, but we leave the bytes intact. So we just send whatever we had before parsing, and we output that. That allows someone to go afterwards and clean it up, for example. So that's the dead letter pattern being used in conjunction with multiple outputs. But of course, multiple outputs can be used in many different ways. Another one that we want to often do is enrich data. So let's imagine that we have that data that's coming in as JSON with the item IDs. And that also includes the store that it was sold in. But the store is an ID, it's a number. So a very common thing we might want to do is enrich the data before we go forward. For example, you may be sending this on to an inference call straight away after this. What we want is we may want the store location or the lat long, as well as the state, etc., to be added to the data set. So side inputs are a way that we can do this. It essentially allows us to create things like maps that we can look into, and that map is sent to all of the hosts where we have the elements being processed, and we can enrich the data moving it forward. Up until this point, we've been mainly concentrating on the primitives that are whether it was a streaming pipeline or a batch pipeline are all being possible to be made use of. But when we move to streaming pipelines and we want to do things like counts, etc., we need to know when to materialize results. For that, we can use windows and triggers. I'm not going to go through triggers. That's another topic for today. But in terms of windows, we can apply various types of windows out of the box with Beam to the data. First is fixed windows. So these are discrete chunks of time that we apply, and that will be applied across the keys as we see within this diagram. Or sliding windows. Sliding windows is great for like moving averages and things like that. So essentially, you've got a window of time that's actually sliding based on an offset that you provide. Another type is the session window. So session window is a data-driven window. Let's imagine that we are trying to sessionize when Reza is on a shopping application, and we want to break up the time that I bought my stationery from the time I bought something else. Now, one way we could do this is actually just use time gaps in the data. So I come on a session, I buy something, and then like 4 hours later or 6 hours later, or maybe a day later, I buy something else. That's a very easy way of actually breaking apart these sessions. And out of the box, you can create a session window and you give it an air gap. And that air gap is basically as long as there's data coming that doesn't exceed that air gap, it considers it as one session. If it goes beyond that air gap, then it creates it as 2 sessions. Now, one of the powerful parts of Beam is the fact that it actually understands and makes use of things like watermarks for event versus processing time processing. Essentially, when we get to see data compared to when it actually happened is very often skewed, right? Now, this could just be skews within the data processing systems, the web servers, etc., that may be sending information to our publish and subscribe API, maybe delayed, maybe a worker failure restarts, it sends information. And in the real world as well, of course, you also get things like mobile phones, which will lose connectivity, which will be offline before the data arrives. So what we can do with event time processing is we try and account for the event time when we're doing our computations rather than when we see the data. So when it actually happened rather than when we see it is when we're trying to do the accumulations. And the way that is done is through watermarks. Now, watermarks is a massive subject. There are actually quite a few papers by the team, the DevFlow team out on this subject. There's a great book by Reuven and Tyler on watermarks. Essentially, I think the key insight is watermark is our intuition on how much of the data we've seen, how much of where we think we are in the data. So do we think we've received all the data we're going to, and therefore we can emit? And when it's based on data that's coming from within the system, it's very accurate. When it's based on systems from outside, we have heuristics and stuff that try and estimate the right thing to do. And again, a deep discussion point with plenty of material on the websites and stuff around this. So how would we change our initial pipeline if we wanted to bring in streaming and windows into the mix? So initially, we need to change from our bounded sources. So rather than our files, we're now reading from PubSub, which is Google Cloud Publish and Subscribe API. So now we're getting a continuous stream of data rather than reading files and processing them. In the next pieces, the core business logic remains pretty much the same, with the exception that we apply window. So we're windowing into fixed windows of 10 seconds on that step. And the interesting thing to note is when you apply a window, it doesn't actually do a grouping function at that point. Applying the window doesn't group the data points together, it tags them. When it first hits the first combiner or group by afterwards is when the actual grouping operation happens. And that's where, so this will change to being the top 10 within our fixed window. We mentioned about the benefits TFX gets by running on top of Beam, anything about the ecosystem around Beam. So some of the things that are interesting, some of the runners are able to do something known as liquid sharding. So here, if we look at the typical workload of a worker when it's getting a parallel work distribution, what we really want is a worker to have an even distribution of the work. So all workers have an even amount of time of work where when they're done, all of the work is complete. How will we know that that's not the case in real world? Different keys have different sizes. We're going to get different workloads. Some things may take longer, some things may take quicker than expected. So what you end up with that jagged line on the bottom right in terms of the work that is assigned to a worker. So the runners that are capable of doing dynamic work rebalancing, here they rebalance the work across the workers to smooth out the distribution of the work. And again, TFX making use of Beam is automatically going to get this whenever a runner is able to support this kind of thing. Something that's not available yet, but is coming soon, it's being worked on by the Beam community, which is really interesting, is around the cross-language support. So here the idea is that you can have a pipeline. I work in Java, so I could have a Java pipeline, and there's a cool library I want from Python to make use of. Being able to use the Python library, the Python transform within my Java pipeline. So it would allow us to do something like this. There's a Java pipeline. I have a bit of Python code, or potentially Go or SQL, giving me access to the various libraries and stuff from that ecosystem, all within the context, again, back to that ethos of giving the developer, allow them to work in the environment that they want to, allowing me to stay in Java while pulling in all the interesting things that I want from Python, etc. And the other advantage of cross-language support, so Java came to Beam first, and it's had many more years of usage and development. So it's got a lot more connectors, and Python is now catching up. But the nice thing about cross-language support is there will no longer be a need to do the catch-up phase. Anything that's available in Java, we will be able to directly make use of in Python, and of course that automatically makes it available for anyone who wants to build, for example, a custom example gen that Rob talked about within the TFX piece. Finally, just something that was newly added. I'm not sure, Rob, if you got this covered in your piece, but the TFX BSL, I just recently started playing with this as well. It allows us to do inference, the run inference piece directly against the save model locally or within a remote execution. And what this allows us to do is run predictions on the pipeline. So we can do all our enrichment, etc., within the pipeline itself. And I'm particularly interested in the streaming aspects of this. So we can do that in stream mode and then run the inference against the data, particularly in enriching the data as it moves forward. And okay, so that was a very high-level overview of Beam. Hopefully, it gives you the good grounding as we go now into Robert's details on TFX. Over to you, Robert.
Okay. Yeah, there you go. All right. Can you see my slides?
Yes.
Okay. All right. We're going to talk about TFX and specifically the components of TFX. So TFX is made up. It's a pipeline framework. Each of the steps in the pipeline is a component. The components conceptually are there's three pieces: the driver, executor, and publisher. The driver and publisher are largely boilerplate code that you probably won't change, but you could. The executor is really where you do your work, and as you might sort of be picking up, you can create your own components here. You're not limited to what TFX gives you out of the boxes, which, by the way, TFX is open source, and all of these pieces are open source, Apache Beam as well. So what is a component? Well, a component and the metadata store interact very closely, and there's a configuration that you set up for components. Many of them are completely configuration driven. But the input for a component comes from the metadata store, which we'll talk about in a little bit. The component does what it does, and then the result is placed back into metadata for other components to use. When it reads from metadata, it reads over a channel, an input channel. So you'll see that abstraction when you start developing components. And similarly, when it writes out to an output channel. So that's how components communicate with each other. You'll have an upstream component that will do something. Maybe it'll read in a data set or calculate statistics or something. The result of that is put into metadata. Components that depend on that result or that artifact will then have their dependencies met, so they will begin to run. They'll pull that from metadata, do their thing, put their result back into metadata. So all of this needs to be orchestrated because we have multiple tasks running, and often, especially in a Kubernetes environment, over multiple nodes. So this needs to be orchestrated. You have several different options for orchestration within TFX. One of the things that we've tried to do in the design of TFX is to make it open at several different layers. One of the layers is at the orchestrator level. So out of the box, when you just do the pip install, TFX will support Airflow, Kubeflow, Apache Beam being used as an orchestrator, which is a little unusual. And there's a fourth one as well that we'll talk about in a second. But I want to emphasize if you have a different orchestrator, so for example, if you wanted to use Luigi, you could write code to extend TFX to use your orchestrator. At the end of the day, you will end up with the same thing. It'll just be represented differently and managed differently, depending upon the orchestrator that you choose. It's going to be a directed acyclic graph, or DAG. So that is the structure from a graph perspective. That's the structure of what a TFX pipeline is. There's also kind of a special orchestrator that we use. It's called the interactive context. And that runs completely in a notebook. So if you think about what an orchestrator does, it sequences tasks and runs them. You're doing that in a notebook simply by executing notebook cells. So as a development tool, it's pretty useful. And you'll see if you go to the TFX website, a lot of our examples, I think maybe most of our examples, use this as a device because it's a great way to do development and also a great way to learn to use TFX. You wouldn't obviously use that in production. Okay, so ML metadata turns out to be a really important piece of this architecture. So what's in metadata? Well, fundamentally, artifacts. Artifacts are kept in metadata. And artifacts have a couple of different things. They have properties that are associated with the artifact. For example, the artifact type. And they also have a payload. So in the case of say, a data set, which is an artifact, the payload for that will be the data set itself, which is kept in storage somewhere. So part of this is kept in a database, part of it is kept in storage, and then you have a URI that points to it. A trained model, for example, is a type of artifact. Artifacts are grouped by the execution run that generated those artifacts. So when you're trying to do analysis to understand the training runs that you did maybe yesterday or 6 months ago, understanding that grouping of the execution run is important. And you can also trace data provenance across the execution. So what that means is I have a result. What component generated that result? And what were the inputs to that component? And so forth. So you can recurse back through the chain of artifacts and components to understand the provenance or how that artifact was generated. That can be very important in a lot of situations, especially for explainability. and in some cases legal requirements. So finding out which data a model was trained on is a very typical usage of data provenance. Also being able to compare, the characteristics of your different training runs. So this is showing TensorFlow, or I'm sorry, TensorBoard, being used on two completely different training runs. They could be, years apart. But if you're trying to understand how change happened over time, why your training run is different today than it was at some point in the past, being able to make that comparison is important. And then there's essentially caching. So if the inputs to a component haven't changed and the configuration hasn't changed, then you don't really need to run that component again. And TFX, keep in mind, is designed for large payloads. Doesn't have to be large payloads, but it's designed to handle large workloads. So we could be talking about terabytes of data that take hours to process in a single component. If you can avoid running that, you want to avoid that. Also, carryover state, the big example of this is warm starting a model. So if you've trained your model for 10,000 epochs and you decide you want to continue training it, being able to do warm starting is important. So there are standard components when you just do a pip install for TFX. There are standard components that come with it that gets you started. But I want to emphasize, you will have most likely needs in your particular domain or application that you'll want to create your own components for. But let's talk about the standard ones because that's where you get started. And let's try to understand first how TFX and Beam are connected to each other. How do these two things work together? Well, you have a component in TFX that could be running on a single server somewhere. It could be running in Kubernetes on a cluster. So it could be either running in a full OS or inside a Docker container. We're going to add Beam to that, and we're going to send it a Beam pipeline. So the definitions of pipelines, the syntax that Reza was just showing you, we're going to put one of those together and send it off to Beam for processing. Beam is going to translate that into whatever target environment you're actually running. So remember, Beam is a sort of a translation layer to a underlying distributed processing framework like Spark or Flink or Cloud Data Flow. So it's going to express it in whatever API is required in that target environment. That target environment is going to use its compute resources to process that set of operations, and it's going to deliver the result back to Beam, which is then going to translate it back into the Beam syntax for your component to use. So from the component perspective, I'm only talking to Beam, but I could be talking to Beam to a Spark cluster or a Flink cluster or a Cloud Data Flow managed service. And all of that is sort of hidden from me. It makes portability and migration really powerful. So that's really how Beam and TFX work together. It's that ability to leverage all these different environments. And in a large organizations, you may have different teams that are using different clusters, or you may be doing acquisitions where you bring in a new group that's using a different cluster, and the fact that you don't have to rewrite your code, that's a big plus. So this is kind of the canonical starting TFX pipeline or DAG. On the left here, we are ingesting, I don't know if you can see my pointer or not, we are ingesting data, and then it passes through these different components. We'll talk about these in a little bit. And on the right, we have different deployment targets. So you can take the same exact model and deploy it in an online serving cluster. You could take that model and use it in a native mobile app in TensorFlow Lite. You could use it inside a web browser with TensorFlow JS or maybe in a Node.js environment. You could also just take that trained model, save it, and then use it for transfer learning or for generating embeddings. And on the bottom here, you also see a separate pipeline that's used for doing bulk inference. So if you're just going to do inference on a lot, a whole batch of requests offline, which is fairly common actually, then bulk inference and the bulk infer component are really useful for that. So now let's talk about each of the, if we go back here, each of these components that we just looked at, we'll go into some detail. So example gen is the beginning of the pipeline. Example gen is what ingests your data set. And there's several of these because the data source that you're ingesting from will be different. This is showing a CSV example gen. There's also, you can ingest from TF records with a different example gen. You may write your own custom example gen as well. So depending on your data source, but example gen is going to do really two things. It's going to ingest your data and convert it to the native format that we're going to use, which is the TF example format in a TF record file. And it's going to split your data set into whatever splits you need, but typically it's at least training and evaluation. And it's going to use Apache Beam to do that. Statistics gen is the next one. And what statistics gen is doing is trying to do descriptive statistics across your data set. So it's going to make a full pass across your data, one full epoch. And the configuration for this is, as you can see, very simple, although it can be more complicated than that, but this is sort of the basic configuration to get you started. And coming out of that, we have statistics which can be visualized with the tools that come with TensorFlow data validation. And that really helps you understand your data set. So I don't know if you can see my pointer, but for this feature here, trip start hour, we can see that we don't have a lot of examples at 6 in the morning. And that's kind of a red flag that we probably need to go out and get some more examples at that time of day. Because if we're going to try to make predictions at 6 a.m., we might not do too well. The next component is schema gen. And schema gen is kind of interesting. It takes the results from statistics gen and it infers the types of your features, including for things like categorical features. What are the valid values? What are the valid categories in that feature? And things like, is it a required feature or optional? Now, it's going to make a best effort at inferring what your schema should be. But you need to inspect that. And as you can see, you have visualization tools to do that. And then if there are things that need to be adjusted in your schema, you want to curate that schema to get it right for your data because it's going to be used downstream by other components. Example validator is taking those results and looking for problems. So it's looking for things like examples where a feature value is the wrong type, or maybe it's missing altogether, or maybe you have a categorical value that is so rare that it really, it's kind of suspicious. It maybe shouldn't be part of that that categorical variable. So it's looking for problems that and warning you about those. But it's up to you to pay attention to what it tells you, and use some domain knowledge to decide, is that a problem or not. Transform is one of the more complex components, as you can kind of see from this example code. The configuration for it, and if you go back here, you can see for all of these components, we're really just configuring these components. They're configuration driven. But for transform, we have to supply some code. So that code is, because what we're using transform for is feature engineering. And the types of feature engineering that you want to do for your data are really going to depend on what's the nature of your data and what does your model need and what kinds of things do you need to do. You could be doing very complex things in feature engineering, or in this example, we're just doing, basic normalization using a z-score. So it's going to take the results of all of those components that ran before, along with this code that you provide, and hang on, and generate its results. So it's going to transform your data set. It's going to do that feature engineering, and it's going to use Beam once again to do that. And this is using the TensorFlow transform library. There's a number of libraries that are available here. I just want to mention those can also be used by themselves. So here we're using transform as a component within TFX, but you could also use TensorFlow transform by itself as a library. One of the key features here, though, is that transform will create a graph, a TensorFlow graph, which has operations in it. And those operations are really two different types of things. They're constants. So for things like the standard deviation of a feature, that really doesn't change from example to example. So that's going to be a constant that it's going to apply. And then operations. So for things like normalizing, you have to do that separately for each example. That graph then gets used both when you're training your model and when you're serving your model. So this avoids the really common problem in production ML of training and serving skew, because you have to do the same feature engineering both when you train and when you take requests for predictions to your model. You have to do that transformation in both places. And in many cases, people don't use the same code. They may even use different languages, and they try to do the same thing in both places. And hopefully they get it right. But rather than take the chance, we use the same exact TensorFlow graph as a pre-processing graph in both places. And that just eliminates that problem. Plus, you only have to write that code once. Trainer is really all about training a model. So it's going to be using TensorFlow to do that, at least in the basic form. And it's going to use the results from transform that we just looked at. It's going to use the schema that was generated. And it's going to produce a result as a saved model, which is a standard format for saving a trained model. And then that's going to be used both for evaluating the performance of your model and for serving it in any of those deployment targets that we looked at before. So a serving cluster or a mobile application or JavaScript application. So that saved model is a nice standardized form of your training. And the configuration for trainer is about what you'd expect. It's things like the number of steps and where to get the transform graph and that kind of thing. The code for training it, of course, is going to be your model and your training code itself. So that is really, when you started this whole journey, maybe that was your focus. You were thinking about that model. So this is where you're going to plug that in. We also, because we're in the TensorFlow ecosystem, we have the TensorFlow tools like TensorBoard here, which in the case of TFX, it's nice because you can compare these model runs like we looked at in the past in previous slides. So understanding how your model changes over time. Once you get into a production environment, you'll discover that you train your model at the start of its life. And then as your data changes, as your business changes, as your needs change, you're retraining that model and maybe re-architecting that model for the life of that product or solution. So being able to compare what you did now with what you did in the past is really important. The next component is evaluator. And evaluator has really two missions in life. First, it evaluates the performance of your model at a deep level. And what I mean by deep is that it's not just looking at a top line metric. So for example, if you're doing a regression, it's not just looking at your RMSE for your whole data set. It's looking at individual slices of your data set to understand how the performance is different for different slices. Those slices really depend on the domain that you're working in and what makes sense for that domain. So it could be the hour of the day if you're working with something that is sensitive to that. It could be different groups of customers. It could be different parts of your product line. However, it makes sense in your domain to slice that data. That's how you want to analyze it. The other thing that evaluator does is it makes sure that you can actually resolve that model. So or validate that model. So it wants to see, is that model better or worse than the model that I currently have in production? So if it's the first model that you've trained, of course you have nothing in production. But if it's any model after that, you don't want to deploy that model if it isn't at least as good or hopefully better than the one that you already have. And if you've been around ML enough, you'll learn that um, just because you trained a new model doesn't mean it actually improved in performance. It often goes sideways, and you discover that you had a problem. So you don't want to deploy that. You want to make sure that you only have good models that you're running in production. So there's some visualization tools. This is part of TensorFlow model analysis. This is another open source library that is used within TFX. And again, you can use this by itself as well. Pusher, if the model is better than the one that you have in production, then Pusher will push it to the whatever deployment targets you've selected for this pipeline. So that could be your serving cluster, that could be your mobile application, whatever it is. There's also another component here, infra validator. I'm not sure, do I talk about that? Not too much. Infra validator is just making sure that your model will physically run on your system. So it's going to try loading your model and just running a test example against it just to make sure that it's actually runnable. Because especially when dealing with things like GPUs and other accelerators, you can easily train a model that exceeds, say, the memory of your GPU. So you want to avoid that, and infra validator allows you to do that. There's also bulk infer, which we looked at a little bit earlier, where if I have a batch of examples that I just want to run offline, bulk infer lets me do that. Okay, so we've talked about components. Within TFX, there are also nodes. So what are nodes? Pipeline nodes are really special purpose classes, and they're used for interacting with metadata. So they do things like if you want to pull in an external artifact into metadata and use it in your pipeline, or if you want to look into metadata and perform queries. So if you're pulling in an external resource of some kind, some sort of data or object, your importer node is available for you to do that. And the main things you need here are the URI of that artifact that you're going to pull in and the type to assign to it, because we need to know what type these artifacts are. Resolver node is used to do the queries. And resolver node, well, you have to define the query that you want to do. And there's different types of queries, like this is looking at the latest artifacts of a particular type and a particular channel. So this is which channel, remember we talked about channels earlier, which channel should I look for that artifact in? So these are tools, and you'll see them used, for example, Evaluator uses one to interact with metadata in sort of special circumstances. So these are the two nodes that we have currently. There's going to be more coming, and of course, this is another place where you can extend TFX. So those were the standard things that you get when you just do a pip install. Let's talk about what it means to customize a component here. So yeah. Actually, we're sort of getting low on time here. Reza, do you want to jump into your demo from here?
It's okay. I think that we're a bit over time to do the demo, and I think this is probably useful for you if you wanted to conclude on this one, to getting the customer
Okay.
piece in.
Let me go through this. So you can extend your existing components. That's an easy way to make a new component. So if you have an existing component that takes the same inputs and outputs that as the component that you need, that's a sort of an easy way to create a new component. Or you can create a fully custom component. To override an executor and just extend an existing component, this is the kind of thing that you're doing. It's just extending the class. And then you plug that component into your pipeline just like any other component. All right. So now going back to Apache Beam, we've talked about how Beam fits in and the different target platforms that it supports and the SDK and languages that it supports. And now, yeah, why don't we dive into the demo? And if people can stay, that's great. I don't think we're going to get kicked out of the room.
Um,
So,
So actually, we are at time. For the demo, what I was going to do is run through one of the quick start guides on data flow. So if folks wanted to give that a try, it's on the Google Cloud Data Flow site, and a beta feature that's been added is the notebook capability. So there is a great example of being able to do a streaming word count, which shows some of the primitives that we were talking about earlier on building a pipeline within the context of an interactive environment. And the cool thing there is before this was available, you had to pretty much build your pipeline and then you submit it and get the results back. Here you can actually submit pipelines as you're building them and materialize results and explore them in the same way that you would do your normal Python development on a notebook. So that quick start is available. And I think we can, Azimar, maybe spend a few minutes on Q&A if there is any questions.
Sure. Thank you, Robert and Reza, for your presentation. I hope everyone enjoyed it. And we have one question saying, when should we use TFX for input processes and when should we use tf.data? They seem like they serve a similar purpose.
yeah, that can easily be confusing. So TF data is really focused towards simply training a TensorFlow model. So if you're ingesting data and you just want to train a model, TF data and the service that it provides for distributed processing, it's really useful for that. But there's a huge difference between that and something that you're going to deploy to production. So all of the things that we talked about for monitoring your data and understanding how it changes over time, doing evaluation of your data at a deep level, and training your model as well. That's all much more important in a production environment. But working with a large data set, TF data is great. Well, it's actually great for several different things, but really more just in a typical model training scenario.
Okay. And I think this is a question to Reza. Could you share the link to the quick start?
Sure. Let me just bring that up.
And while Reza is doing that, I don't think we have any other questions so far. And another reminder for everyone who is here, please fill out the survey because it's very important for us to build future content. And if you would like to see like Reza's demo or some other demos, like please let us know in the survey. And thank you. People are sharing that it was great presentation. Reza, I hope you have a good night. And Robert, have a good day. And thank you all for coming to this session. And again, this links to the slides and recordings will be shared on the GitHub repo called Beam Learning Months. So thank you.
I just can't find the link at the moment. I'll give it to you and you can share it on that same GitHub repo.
That's excellent. Thank you.
Thanks.
And
Bye.
yeah, bye.